Yeah, thank you very much for the invitation and that I can talk here. So yeah, this is joint work with my supervisor Sebastian and Sven Wang and Josef Mazuk from MIT. And we also, we had a nice introduction already to why you would want to make infinite dimensional models work today in the morning. And I actually asked, so I have a few, I don't know if I want to start this or if hell will break loose, but I have a few plots on the discussion of yesterday. If you want to see, I could do it now very quickly or afterwards or not at all. I don't know how big it's about. I mean, I can show it very quickly, maybe to. Let's do this. Okay.
Yeah, let's do this.
Okay.
Yeah, okay. When Sebastian left.
Okay, yeah, so I'm gonna give a quick introduction to diffusion models. I'm going to take lots of time because the last one was a discrete time, so I have to do it in continuous time once more to get it even. Then a very quick introduction to infinite dimensional Gaussian measures, and because this is maybe like the main prerequisite for the infinite dimensional diffusion models, and in the end some plots. Okay, so we really don't need this. Nice picture from Yang Song's blog, not the animated ones like Emil and Valentin had. Okay, so forward SDE I will denote by xt. The marginals of xt are denoted by p. P0 is our target distribution, so the numbering basically t goes forward from target to normal distribution. The reverse SDE is denoted by yt. It will fulfill this SDE, which is has exactly the sign flip of the forward SDE in the drift, then also some Brownian motion, and this term, which you can see as basically nudging the particles into the right area of space. Basically, this term will, in some sense, cancel out the white noises in both directions. And the marginals of the backward SDE are now questioned. But I don't think we will need that. So xt forward, yt backward, pt are the marginals of xt. Yes, so the goal is to simulate the reverse SDE. We had this also already a few times, so I'm going to be really quick with this. So if we could simulate this, so we could start it. Actually, I'm just going to go to the image because, so basically, also very similar image to what you've already seen, not in animated, but therefore two images this time. So we have some complicated, or like complicated here, one-dimensional target distribution that we want to sample from. We start the forward SDE in this target distribution. If we diffuse it, it should be diffusing towards the normal distribution. But of course, it only will reach the normal distribution in infinite time, and we will stop it at some finite time where we actually haven't reached it, especially in high dimensions, maybe. Although that, I mean, the convergence is quite quick. But this is to exemplify that there's one mistake here. So if we would be able to start in this distribution, which is close to a normal distribution, and then run it backwards, and we would just run backwards this heat maps, and in the end land in our perfect distribution. But because we don't have access to this P1 distribution, because it still depends on the initial conditions in some way, we just say, okay, it's close enough to a normal distribution. So we switch from the initial conditions, this a bit messy distribution, to the normal distribution, start the reverse SDE here and run it. And then we also have some approximation around the drift, so we don't have the perfect reverse drift. We did there you do this neural network approximation with the denoising score matching loss. And then in the end, you will land in a different distribution than the distribution that you actually started from, but maybe it's similar enough. 2D. So you start from a normal, and here you see nicely how it then. So it was trained to be the uniform distribution on the sphere. And here you see how it transfers from a normal distribution to the sphere. Okay, and we're already at the infinite dimensional part. Any questions about diffusion models? Anyone bold enough to now ask about the basics? But okay, so how do we do it in infinite dimensions? So the main thing is what we had here, we wanted to converge to a standard normal distribution, right? So we had an Ornstein-Uhlenbeck process that we started somewhere, which was converging to a standard normal distribution in Rn. And it's not so clear anymore what a standard normal distribution is in infinite dimensions, because what's the normal distribution? So a standard normal distribution means that your covariance in some sense is the identity, or that if you pick some orthonormal basis of your space, that in each direction you have independent noise of the same magnitude. And this, of course, very much depends on which space you pick. If you pick a space with a different norm or something, you will get a different orthonormal basis. Maybe they will be shorter or longer or something like this, the vectors, or go in different directions. And if you now put independent noise on them, you will get a different kind of standard normal distribution. So in some sense, in infinite dimensions, the question of choosing a standard normal distribution is very much related to the question on which space do you want this to be standard normal. So yeah, and you can also define it like this. So basically, so this is a bit heuristic. I'm not going to go into too much details, but for each Gaussian measure, you can associate, for each Hilbert space, you can associate the Gaussian measure so that for any two elements of this Hilbert space, you can also view them as linear functions, right? Just the scalar products with these elements, the covariance of the push forward in this direction and the push forward in this direction is just given by the scalar product in this space. Yeah, this is the same thing that you would have if you would just use the standard normal distribution in Rn with identity covariance matrix, and then you would take two vectors and check the covariance of x projected onto v and x projected onto w. Then the covariance would just be the scalar product of v and w. Yeah. So yeah, this is the same thing as in RD. And one problem in infinite dimensions is that this measure that is now standard, maybe here should be U actually, that's a standard normal distribution basically on the space U, will not be supported on U anymore. So in Rn, you can just pick the standard normal distribution on Rn and you will get a random variable which takes values in Rn. And in infinite dimensions, if you take, like basically take your Hilbert space, for example, L2 or H1 or some whatever Hilbert space, and put a standard normal distribution on there, you will need, this thing will take values only in a larger space. So mostly to do mathematical analysis and stuff, you always have to like look onto pick some larger space in which you then view the whole process or the whole random variable. And there's also no natural choice for that normally. There's like, because you can always go bigger, of course, and one could think, okay, maybe there's a smallest space on which this takes place. And normally it's not. It's like an inequality. So there's not one smallest natural space that you can think. Okay, so the main takeaway is that the choice of the Gaussian measure in infinite dimensions is equivalent to picking the smaller space on which you want the Gaussian measure to be a standard normal distribution. And this space is also called the Cameron-Martin space or reproducing kernel Hilbert space. Depends on the literature. So actually they're a bit different, but isomorphic, but both of them are basically this. So a nice picture to exemplify it again, you have this small space, the Cameron-Martin space U, on which you have the standard normal distribution, and then you pick, this is the choice, the larger space H, which contains U on which your Gaussian random variable actually will take place. And on this bigger space now, so because what I do basically, so in some sense, what you do is, okay, let's say this is an infinite dimensional space. And then you would pick a standard normal distribution. So it would basically have variance here, 1, and a variance here of 1. And what you now do is you just rescale basically the vectors. So you say this doesn't have length 1 anymore, but it's actually a much, if you go bigger, it has to be a shorter vector basically. And then also the variance of this decreases. So basically, this thing that is standard normal on the space U will then on this larger space have a covariance matrix C. This is maybe the main takeaway. So the covariance matrix gives you, because it's basically what you plug in, like linear algebra wise, it's just the change of your scalar product to make it the right bilinear form. Yeah, so
The way I've seen it is, you pick your age that you're seeing, you can define your view based on that.
yeah, you can also define it like that. I mean,
There's no
maybe it's nicer for actually, yeah. The thing is, you don't, because the age is so arbitrary, I think it's nicer to have it in this way, to have it just a standard normal. So U is in some sense actually the inherent thing that you choose, and then you pick an age which is kind of arbitrary to look at the
In
thing.
your case, you pick your C and you figure out the age, or
I pick my U,
Yeah.
and then if you pick any on which it would be the identity covariance matrix, and then I pick a larger space, and on this, and then by the choice of this space, I can, because this measure is now uniquely defined, I get a covariance matrix of this Gaussian measure on the larger space. And on this larger space, it will be now a compact operator, which decays very quickly in the eigenvalues.
So you has to be finite.
No. U is infinite dimensional. So what is here? So what, for example, you can think of H being L2. So you have, and then if you would put actual white noise on L2, you would get something really horrible, right? So it would mean that every point in of your function is completely uncorrelated to every neighboring point. So absolutely non-continuous, actually not a function anymore. So to actually even make sense of this, like, white noise thing, you would have to go to some negative Sobolev space and view the thing there in some sense. Or if you want, for example, a Gaussian measure that takes values in L2, you can go to a smaller space. For example, if you take H1, so the derivatives, the Sobolev space H1, which is the scalar product just taking the derivatives, and you basically want something like the standard normal distribution on the derivatives, you would get the Brownian motion. And the Brownian motion would then take place on L2, on the larger space. This is like, yeah, you wanted to say something?
No, yeah, so U is the people space. What is funny is that, like, when you do PE, basically you search for a smaller space, people be defining the Laplacian, then you choose H1, and then you have the bi-duality, you have the H minus 1. When you choose the covariance, you just choose the same people space, then you search for a larger space, and by duality you have a smaller space, which gives you the different people. And so, and what is yeah, basically, and that base and what is, and since we know that the covariance corresponds to the inverse of the operator in simpler space.
Yeah. Yeah, I mean, the thing is, so you can also very much just view it as also, as you said, so we could also start with L2, and then we say, okay, we want a Gaussian random variable that takes values in L2, and then you will see it has to have a covariance so that the eigenvalues decay very quickly. They have to be summable. So something like 1/n squared, for example, on the diagonal. Or just the eigenvalues of C would be 1/n squared. And then through the C you would get a smaller space U, which is contained in L2. And on this, you could view the Gaussian measure as being standard normal. I just saw the problem a bit, because many papers then start actually by saying, okay, we have to pick C trace class. There's no other choice, because otherwise it won't be supported on our Hilbert space. But in some sense, what I don't like about this view is that the choice of the Hilbert space is kind of also a choice. You can just go to a larger Hilbert space and then you can do the same thing as before. So just saying I have to pick C trace class white noise doesn't work in infinite dimensions is not true theoretically. So it's just a matter of in which space you view it. This is why I'm trying to introduce it like that. But on the other hand, you can also just see Gaussian random variable in your Hilbert space of infinite dimensions. The covariance can't be any matrix anymore, but it has to be something that decays very quickly in the eigenvalues. So basically has not much noise in the letter coordinates, which is maybe, I still haven't found a very nice way on introducing this, obviously. But yeah. Are there any questions? Yeah, okay. Okay, so choosing a Gaussian measure is equivalent to choosing a space on which you want to have the standard normal distribution. And then often for mathematical analysis, one needs to choose the larger Hilbert space on which things take place, on which you then have a norm to maybe like, yeah, measure distances. Okay, now we actually will just fix some larger Hilbert space H, which is arbitrary though. And we look at the problem for the forward SCE in infinite dimensions. And the first thing is this. Now, like what is actually, so which Wiener process do we choose here? It's the same thing as with the Gaussian measure. So Brownian motion normally has basically increments that are standard normally distributed. So IID normally, like, yeah, standard normal. And the same thing will appear here. We have to choose a covariance operator or a specific Brownian motion that we want to apply. But maybe from now on, we will also just, this should be a square root. We will just choose C, which is the covariance of the normal distribution that we will converge to. So in some sense, you can, we fix now the Hilbert space and we choose a specific Gaussian measure on a smaller space. And then we choose this forward. So this is basically just a choice in the forward SDE now. So we start from our data distribution and we're in finite dimensions. We always just said, okay, now we go to the standard normal distribution. We now have to make a choice to which normal distribution do we go. And this choice is equivalent to choosing the covariance operator of this normal distribution. And then we also have to choose the covariance operator in our forward SDE. Yeah. So the square root of C? Yes, this has to be a square root, yeah. And V is now space-time white noise. Yeah. Obviously speaking. Yeah. Of the it's the space-time white noise. Yeah, yeah. Yeah. Okay, so this is the problem basically with the forward SDE. What the thing that we had to do is choose which kind of white noise you want to have, which kind of Gaussian noise you want to have, or the covariance operator. And in your talk, this would have been choosing the covariance of the covariance kernel of the Gaussian process that you want to have. So instead of adding white noise, like maybe if we view L2 where we just have uncorrelated noise, this covariance operator gives us some correlation structure in space, and we will now add Gaussian process noise at each step. And now the problems with the infinite dimensional case. So now we have this, we already changed the Brownian motion. And another problem with just writing down this SDE in infinite dimensions is this, because this here is the density of the marginals at time t with respect to the Lebesgue measure. And there's no Lebesgue measure in infinite dimensions, so it's not really clear what this expression even means. Yeah. Or if it's well defined. At least we know that PT itself is not well defined, and we will try to make sense of gradient log PT at least. And a nice aside is now, just for the people who are into infinite dimensional stuff, is that this can actually be identified as, or in finite dimensions, this looks like this would be the gradient not with respect to H, but with respect to U in some sense, and this is the U Wiener process. So actually this whole thing is kind of independent of the choice of H of this larger space. So we can write down the reverse SDE actually only by choosing the smaller space. We don't have to make any reference to the larger space, which is kind of nice.
Have you yet made the assumption that the data distributions have to continue with respect to your Gaussian measure, or is it not yet?
Not yet, no. And no, we don't need that, no.
Yeah. Otherwise, the rate of the derivative is.
Yeah. So this, no. I mean, this is not done yet. We're not done at this point. This thing, we don't know how to define yet. This is a Lebesgue density still. So this is still a density to a Lebesgue measure. And we have not exchanged this for anything.
Now, and reverse SDE is really you always have the ratio between the forward and the backward. But if there's a rather independent derivative, we actually have that.
it depends on where you start. I mean, if you start in a Gaussian measure with C and you choose, I mean, I will come to this, and you choose the right covariance matrix, then, but you have, so you could think, of course, I mean, one obvious way out would be like, which is like what people always do in infinite dimensions, that say, okay, we don't have the back densities, we choose a Gaussian reference measure, right? And then we just make everything with respect to the Gaussian reference measure. You can do similar things here, but the problem is that depending on your initial condition, the Gaussian reference measures will be different. For example, if your initial condition is already N0C, then you got, or maybe something with a density for this, then your Gaussian reference measure at each point should be this, because basically this thing won't change your Gaussian reference, and you will at each point have a density with respect to this measure. But if your initial condition is just a Dirac at 0, then your Gaussian reference measure, or something manifold like, should look like basically the forward kernel of the SDE. So something like this. So so depending on the initial condition, like on mu data, you will have different natural reference measures for this PT. And these two are singular in infinite dimensions already, because same covariance but multiplied with a scalar, and so it's yeah. So this is one way, and other works do this. I mean, there are other works like the one with all the authors from NVIDIA. They just assume it's like the beginning is Gaussian and it stays Gaussian, and just everything Gaussian. Yeah. So, and then in finite dimensions, what we have is Tweedy's formula actually. So we can rewrite this drift term actually. So this nabla log PT as a conditional expectation. And now we just use this as a definition of the score in infinite dimensions. So basically the way, because the conditional expectation can be made sense of also in infinite dimensions. So of course you have to choose a version of it and stuff, but it makes sense. And you can just use it as a definition of the reverse drift in infinite dimensions. And then you of course have to prove that stuff still works out.
I'm not going to put this question. I thought it would need to be why isn't PT the density coming from the forward number than the first one?
Yes.
So but you're using here the you're reversing it from next to 0.
Yeah, so basically what this does is it looks, I mean, you have to prove, of course, that this holds, but this is a known result in finite dimensions that it holds. And what it does is basically, so at PT, I mean, you start with some complicated distribution, right? And then you diffuse to something nicer, but this diffusion is basically what it does is it kind of looks, I mean, it takes the average of all the points that landed here. And in some sense, the same thing holds for a gradient. So you basically, to get the gradient of your probability at time t, what you do is kind of you look where you came from with which probability.
Presumably, you need to first define that object that you're the equation that you had before. You were using that object, which you haven't defined. Now you're saying that this object is equal to this thing.
In finite dimensions. In finite dimensions, we know this holds.
Yes.
In infinite dimensions, this can be made sense of in some very specific cases. But we just say we use this as a reverse drift of the STE. Like we don't prove equivalence or anything, because there is not really equivalence, because this doesn't exist. Yeah. Although there are works like there's this Bogachev differential measures, and if you do it like really, really abstractly, you can actually make kind of sense of this, but it's really, really technical.
In finite dimension,
Yes, in finite dimension it works, and basically we yes,
the left hand side is still have meaning.
Exactly, yeah. Okay, so and now we basically have a new reverse SDE with some covariance operator C in front of the white noise, and with this drift, And then, of course, to show that the algorithm makes sense, you have to show that the reverse SDE has a solution, that it has unique solutions, and we also do upper bounds on the Wasserstein distance between the sampled measure and the true target distribution. So yeah, because I was afraid that I'm too quick, I put theorems in here yesterday. Normally I don't put the theorems in full length in. But so this is the first, just existence. So now we basically write down the reverse SDE with the, without a comma here, with the new drift. So instead of the nabla log PT here, now we have this S, which we defined before as this conditional expectation.
This conditional expectation is a special, I mean, it's a special case because it's Gaussian, right? TD is Gaussian integration by part somehow, right?
No, it always holds.
Even though if you have non-Gaussian transition kernels,
Ah, you mean the transition kernels?
yeah, have to be Gaussian, right?
Yeah, probably, yeah.
Oh, TD, so.
I mean, the transition kernels are Gaussian,
In this
so
case, they are. I'm
yeah.
just wondering, I mean.
And
that's
they always
essential.
are.
I think it is, right? I mean, otherwise it's not true. It is.
Yeah, it
But
should not
otherwise
hold,
you-
yeah.
Okay. Yeah, I think, anyway,
Yeah.
but I think it's tight. I mean, the transition kernels here.
Yeah, probably. Yeah, I mean, could very well be, but I mean, like the transition kernels are Gaussian
Yeah.
all the time in this. So yeah, it has a solution. And the proof idea for this is basically that you can show that this thing is a martingale in the reverse time direction, which is known and it's really nice. But also if you actually now do the spectral approximations, so you now, so here's a square root C. So now if you do, for the square root C, you can get like a spectral basis, and then you can approximate this SDE with finite dimensional SDEs. And basically the finite dimensional version of the drift will also be a martingale in the space direction, and this helps you a lot with all kinds of convergence. Yes, so there has to be a square root C here, or this is just the C Wiener process of this, like this specific space. Yeah.
This diffusion is always modified, so there is a no condition for the condition, so this diffusion is very defined, or so what, which is a new assumption, or
So that the reverse, so if you time reverse it, that it will fulfill this SDE with this thing, yeah, this always holds. The only question is, of course, if you run it yourself, because it's only defined almost truly for each time, because it's a conditional expectation, then so for the uniqueness, basically, we will prove in some special cases that you can pick continuous versions of this. But always holds, and also, I mean,
so there is no condition and new data, so because so is there a condition in the data to hold any new data, or
I know, so here so the projections of these things on the finite dimensional spaces have to fulfill the assumptions for finite dimensional, yeah. But
projection,
yeah,
projection of projections?
No, that's just a typo.
yeah, I mean, I copied this thing in there like quite recently. Let's say, so you just
So this is a basic assumption of
yeah, the finite dimensional things have, but this is, so the time reversal assumptions are quite weak actually. So this is not really, yeah.
But isn't that sort of related to control? I mean, like, I always get it wrong. I mean, controllability or something, in sort of control theory. Where can you go essentially, right? With an SD and then you control, finite control. There must be also a PD theory. Right? Yeah.
I mean, the thing is here,
Yeah.
but you always start here, right? I mean, you start in PT still here, this thing. So you went with the forward SDE from your data to PT, and then you can also go back with this SDE.
But it's obvious. Or it's just, I guess it's related to your question. I mean, what are the conditions on PT that this is not something you cannot actually want? It doesn't make sense as an initial condition for your SDE, right?
No, I don't.
I mean, I don't think, I mean, your SDE is not defined for any measures initially, right? I mean,
Yeah, I mean, here I'm showing existence for this specific initial measure. This is what I'm saying. So because of
Yeah,
control,
because of
we're
this
not
control
starting
projection
somewhere
stuff.
else in space entirely. And now for uniqueness, then we will do like arbitrary initial conditions and stuff like this. And then you need also some continuity here in the
So the deterministic control you can't go back from the integration from any part.
Yeah.
Start from something which is already a solution of the integration.
Yeah, exactly. Here is the trick that you already know that this path exists. Yeah.
You can regress it.
Yeah.
But you should just be sure that so the truth is that you do it spectral coordinate by spectral coordinate. And how do you deal with the convergence? The fact that there is infinite amount.
This is exactly martingale theory. So the cool thing is that you now get these Sn, they will form a martingale in the spectral thing, and then with martingale they are L2 bounded, and then in martingale theory you get convergence for free basically. And because it's also a martingale in time direction, you not only get convergence for each t, you get actually uniform convergence over all t's in L2. It's
also in n.
Yeah, exactly. It's like the most what every stochastic analyst would wish for, like martingale in every direction.
And so how does this dependency,
Hmm?
or does it dependency, or is choice of operating channel?
The existence, no.
So it works right as the
Yeah,
because still you can choose any seat still. And it
You-
works well.
yeah, you could choose any seat. So the trick here is really we're starting in the right initial conditions, right? So I mean, of course, if mu data is supported on this line and we only take a C that only diffuses in this direction, you have a problem if you then start here, right? Yeah, because then this stuff is not well defined. But we start in the right condition.
So with yes, you start with just inside the around space.
No. I'm almost surely not in the Cameron-Martin. PT will almost surely be not in the Cameron-Martin space of this thing.
But the other forward will be with the around space.
Yeah.
But it's not the one.
The forward basically immediately leaves the Cameron-Martin space because as soon as you add Brownian motion, like as soon as the Gaussian variable itself is not, so you're out of it immediately, and the reverse has to push you back. Okay. Although, I mean, I'm not assuming yet that X mu data is in the Cameron-Martin space, right? Mu data can also be on a larger space. Yeah. So then uniqueness is for two cases, and the first one is assuming that mu data is in the Cameron-Martin space on a ball of radius r, but Cameron-Martin ball. So you take this very nice, strong, smooth norm, and in there, if your mu data is supported in this, we can show uniqueness. So for example, if you use C as the white noise, so as L2 white noise, basically, then it only would need to be supported on L2. But in this case, so this it's like a strong assumption on the support of mu data, or it's saying actually, so if you have a mu data which is supported in some Hilbert space, L2, let it be H1, then you need to use the white noise process of this Hilbert space actually to get uniqueness of the reverse thing. So actually introduce way more noise than you would think in this sense. So if mu data is supported in a ball in L2 of L2 functions, then you would really need to introduce white noise, like the white noise as we know it, where each point is uncorrelated to get uniqueness. But this covers the manifold case because there are no assumptions here on mu data that it's smooth or anything. It can be supported on submanifolds. It can be something complicated. And the other case is when mu data is given as a density with respect to a Gaussian measure. Then we can also show uniqueness. And in both cases, it works by showing local Lipschitzness, basically. Although the weird thing here is that you actually show local Lipschitzness of the drift with respect to the Cameron-Martin norm, even though the drift itself doesn't take values in the Cameron-Martin norm. If anyone has heard about something like this, I would be very interested actually, but yeah. So, and final thing, final theorem is dimension independent distance bounds. So this is a straightforward coupling argument after everything is well defined. And it's just Wasserstein bound on the difference between the measure that you will sample and the measure where your data is coming from. And it separates into three different parts. So again, we have to assume that the drift is Lipschitz now for this two ball. So we have this growing part. Yeah, I mean, that's quite common. Then the epsilon loss, which is just your training loss. So how well you have optimized your loss. The difference in W2 between your initial condition that you would want to start from your reverse STE and the true equilibrium distribution, and then a numerical integration error, which can be bounded like this also with Markov methods. So what you need to assume is that, yeah, basically your in finite dimensions, this would account to saying that nabla log mu data is square integrable. Yeah.
One over the one minus the
Sorry?
definition of S, there's not an explanation for this kind of definition. The coefficient in front of you have x minus 3d being divided by a coefficient that's going to 0.
Yeah, but you can still, for example, yeah, so it looks like it will explode. You mean the Lipschitzness?
As well, but no, I mean more S.
Yeah, and also on this. Yes, this looks like it explodes. And I mean, as soon as your measure is supported on some submanifold, this will explode. So yeah, there's that. But if you actually have something like maybe that it's smooth with respect to the Gaussian measure with covariance C, so it actually has a density, mu data is given as a density with respect to this, then you can show that it actually will be uniformly Lipschitz. Like very similar to finite dimensions. If everything is smooth at the beginning, it kind of stays smooth. As soon as manifold case, I think Alain has a very exciting new work coming up. For, I don't know if manifold case, but for very rough initial conditions for these convergences. Yeah. Okay, now plots. So this is just two-dimensional. What we did is, so we have some prior, all of the plots are inspired by Bayesian inverse problems. So we just take us some prior measure, and then we define an observation operator, and we train the model conditionally. So we give in the observation and the prior measurement. So we sample from the prior, get observations, sample the model conditionally, and then it can sample from the conditional distributions. So in the end, we only plug in an observation and get a conditional sample. And this is a linear inverse problem. So prior was some Gaussian, which was actually, had a very high variance in one coordinate, a very small covariance in the other coordinate, because this is kind of illustrative for infinite dimensions. And then we once just use the white noise model, so identity covariance matrix basically, and forward and backward diffuse with that. And in the other case, we use the covariance of the prior measure actually to diffuse with that. So also what you would have done basically, I think. And then here you have in yellow always the confidence ellipse of the true distribution. So in the end, we then plug in one specific observation and let it run and see what samples it gives us. And because this was Gaussian, linear, we know exactly what the posterior should be. It should just be a new version basically of the prior in this case, and covariance a bit scale. And so the yellow thing is what the posterior should be, and the red thing is what the algorithm estimates. And we see that this one actually estimates it quite nicely, while if we do add noise in the other direction, it totally gets the area right. But it doesn't forget about the noise in the second coordinate fully. So you still have that influence, and it also doesn't get this one fully right. So the covariance structure is kind of preserved. And now a numerical example for nonlinear case. So again, Gaussian prior, now we have a nonlinear observation with the square of the norm so that the posterior will be bimodal. Then again, we plug in one observation. We know the true posterior should look very much like these two here. I don't have a picture of it here. Upper row is, and this is always after training, right? Like, so the longer you train. Upper row is when you do it with white noise and you see that it kind of gets the right thing. And also now with the right covariance noise, and it actually is a bit better because the true distribution also does look very concentrated because the prior was chosen to be like this, whereas this has a bit more of the Gaussian law structure. Now, one infinite dimensional example. So this is from volatility estimation. So we have some function space prior where we put some smoothness on the volatility. Then we generate some measurements and basically observe the stochastic integrals like this here at different times. And from that you get a likelihood, but everything like all overall, it's again a conditional model for the given observation that we put in. This should be the heat map. So this is the x-axis. It should go from -1 to -1.5 to 1.5. And this is time of the function sample. So this is the heat map, how it should look. So you see that the samples are very concentrated in this area, the paths, way less certainty here, a bit more certainty here. So this is just like a way to visualize this distribution. And here are some sample paths with a bit of jitter because we had to add diagonal noise to make the covariance not well defined, to make it for it to be possible to take the square root and stuff. Now I've heard this week, actually, I don't know who gave the talk. I think Anastasia, right? With the, so you can do circular embedding, I guess, and get around this jitter. But yeah, we haven't done that yet. And now we do it once with white noise models. So we add white noise in the path space. And once we add the noise which corresponds to the prior that we've chosen in the Bayesian inverse problem. And you see that both of them kind of get the distribution right, like none of them is really bad. This, I would say, looks a bit more, this heat map looks a bit more like this, the upper heat, like the true heat map and the upper heat map, I would say. But the main difference is in the samples that, so sometimes so that the white noise samples, basically you see the white noise again, you see that actually you've trained it with white noise and it doesn't get the right regularity. So it's some actually in the beginning of the epochs, like at the beginning of training, it seems to actually get it much better than it does it at the end, but then it kind of interchanges from these samples where the smoothness is kind of right to some where, because the distribution is completely off here, to a better distribution, but loses on the smoothness. And while these things here actually always keep the right kind of smoothness. So this is in some sense the same effect of in 2D, that instead of staying on this, you also have noise in the higher frequencies where you actually didn't want to have noise. Because this basically shows you that also in the high Fourier frequencies, in some sense, the thing isn't zero, although it should be. Because, exactly. And this is the plot. So this is just the 20 Fourier. 20 Fourier. Marginal, so we basically put it to Fourier or to the spectral space. The higher frequencies will correspond to roughness. This is the red distribution, is what kind of distribution we want in this marginal. You see that, of course, because we are starting in this distribution and always adding the right kind of noise, with when we do the C covariance thing, we just stay in the right kind of area. While for the white noise, there are some things that are off, but it kind of gets in the beginning, and then in the end, it completely overestimates this marginal. So way too much jittering. Yeah. Okay, and that's it. That would be some sort of preconditioning you do, but choosing the right variant. And not just like what we could be like. Yeah, in some sense, you would say that you're choosing the So yeah, in these cases, basically, you know how your distribution looks, and you're choosing the covariance to be similar. Essentially, yeah, you basically, if your distribution is supported on this kind of space, you're also adding noise of this kind of form and not going out there. Yeah.
So you mentioned that the score can be approximated using Tweedy's formula, right?
Mhm.
In the finite dimensional case. People actually use it in the finite dimensional case. So I guess usually there's a different objective there.
You mean the loss function?
I mean, approximating the score using Tweedy's expectation.
It's a thing that like people do it all the time, like use this kind of yeah, I mean it's a very well-known formula, but I mean I think you're talking about if we can approximate it in a loss function now, like if we can use, so because you can use exactly the same denoising score matching loss that you would also use in finite dimension.
So it boils down to the same thing.
Sorry?
It boils down to the same thing, like the objective and
Yeah, the loss function.
The loss function.
Yeah, the loss function. So I mean, but actually the loss function in the Tweedy's formula case is kind of more intuitive because like, so what we normally do is you write this right now log et minus s theta squared, and then you say, oh, this is actually the same thing as if we just plug in the transition kernel here. Minus s theta, and okay, if we do the transition kernel, actually what we have here is the noise that we used to predict xt, and at time t we want to basically predict the oh, this is a key. Yeah, we want to predict the noise, but I mean actually I mean I think the 3D formula is kind of the more intuitive thing. I mean also if you like with all this flow matching, right? It looks way more similar to this, I would say. But now what you have here is now xt minus x0 given xt. This is the thing you want to, so I'm leaving out all the e to the minus t stuff here, minus s theta. And then it's very easy, like it's just multiplying it out once and then explain using conditional expectation definition that this is the same thing as just xt minus x0 minus s theta squared. So, and this here is just the noise that you use to get xt. So it's kind of, here it really tells, so in one sense, here you say, okay, you want to get the mean, and in the other case, you say it's the same thing as if I do a Monte Carlo approximation of this thing at every step, yeah, and match it to this. So you use exactly the same loss. Yeah. Sorry? They're not, there's a plus C here. Yeah, there is a plus, but yeah, exactly, yeah. But the constant doesn't depend on this thing, so.
Okay, so let's